Hey, Mr. Rainsberg here, and we are looking at lesson 2.2. We're finishing it off with assessing normality. So far in 2.2, we looked at the empirical rule. We looked at 68, 95, 99.7 for amount of information, amount of data, percent of data within 1 standard deviation, 2 standard deviations, and 3 standard deviations of the mean for an approximately normal distribution. We also looked at z-scores and percentiles. We looked at table A. I know Mr. Nichols is making a video that goes over how to use your calculator even for those, if you want to learn the technology aspect for it. So we've learned how to find all the different standardized, the z-scores on the bottom of it. Now what we're going to do is we're going to kind of go back and we're going to determine how do we assess normality. And what that means is if we have a set of data and we want to determine is that data approximately normal. That's what we want to determine. So you're given a list of numbers and you have no idea what the shape of it is. We're going to look at how do we determine that, if it's approximately normal. So normal distributions, they are great for analyzing data, and they come from a lot of real world data that we go through. One of the main things we do throughout this course is as we go further is statistical inference on it. And it's statistical inference based on approximately normal distributions. So we have to have a strategy. And that's what this lesson is about, is creating a strategy for assessing normality. So in my opinion right here, this is the primary focus of this lesson. The data, they do not need to be perfectly, exactly normal. They just need to be approximately normal. What that means is they should not show any significant departures like outliers, heavy skewness, multiple peaks on it. And there are some ways we already know how to do that. The one is what you learned the first day. We learned the empirical rule the first day. We looked at how do we count the number of observations within 1 standard deviation, 2 standard deviation, 3 standard deviations in the mean with the percents. So we learned that 68% is within 1 standard deviation, 95% within 2, 99.7% of the information within 3. We could use that empirical rule. We could calculate what is the standard deviation for the data set. And then we can go, okay, well, what is 1 times that standard deviation plus or minus from the mean? And we could count how many of those observations, how many of those data fall within 1 standard deviation of the mean and divide by the total. And that would give us the percent. And if that percent is close to 68, good, then you move on. We can count how many are within 2 standard deviations of the mean. Divide by the total, that gives you the percent. Hey, great, if that's 95, good, we move on. That's tedious. That's going to take a long time for it. It's not bad. Empirical rule is great for kind of keeping up here and approximating. But for checking for normality, it's going to take a lot of time to do that. So we could try some graphical methods. We can always plot data. Always look at a graph. Do I really have to sketch it? Yes, you always have to sketch a graph. We've talked about that many times. So we can do a dot plot. We can do a stem plot. We can do a histogram. These are really great for looking for approximate symmetry. And also for looking for bell shapes. Those 3 dot plots, the dots will show you. Stem plots turn sideways, but you can still look for symmetry on that, approximately symmetrical with a single mound. And we can also see histograms are really good for that. The one that's not too good for shape when it comes for approximately normal is box plots. Though they're nice to graph and they're really a lot of fun to graph. They show symmetry, but they don't show approximately normal. And those are 2 different things on it. So be very careful on it. Now, the other thing, the new thing, I mean, we could do this. That might take a lot of time. You know, this, not too bad. We've used that before. The new one for assessing normality is a normal probability plot. That normal probability plot is what we're going to use to determine if a set of data is approximately normal. And here's how we're going to go about doing that. So if we have a set of data, let's pull up the answers for it. What we can do is we can plot each observation corresponding to its percentile z-score. So we can plot each observation on the x-axis and plot its z-score on the y-axis. And we can determine from that if it is approximately normal. So if the points, when you do this, if they are close to a straight line, and we're going to say, in this case, if they are almost linear, if they create a linear pattern, So if your lines create a linear pattern, then we could say it's approximately normal. Standard deviations from a straight line indicate a non-normal distribution. Sorry, systematic deviations from a straight line indicate a non-normal distribution. And what that means is if you see it pulling away from a straight line, approximately straight line, then it's going to be non-normal. Outliers are points that are far away from the overall pattern. So right here, you see two images. One of them is a histogram. I look at a histogram, you know what comes to mind? It's right skewed. I can see that. Perfect. That's before. Now let's look at assessing normality with a normal probability plot. And so what I'm going to do is I encourage you, draw in the horizontal line, the x-axis at 0 for it. And that's going to be kind of where the middle is. If you think about a normal distribution, when we sketch the approximate normal curve, right in the middle is your mean. I want to draw the horizontal line so I can show you where the positive z-scores are and where the negative z-scores are for it. And that's what we're looking at. So for this, what I want to realize is I can see here it's right skewed. So what does that look like on the normal probability plot? Well, if I look at that, I can see right here it starts off, and I'm going to use the word fast, is it keeps on plotting points really, really close to each other. It starts off fast. Everything's getting bam, 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 bam. All the information's right there on it. And then what happens is it's going to slowly taper off. And so then it starts to spread out up here. It starts to slow down up here. The points are boom, boom. They're a little spread out more and more. There's even kind of like, you might consider it a tail that's here. There's a longer tail in that positive z-score area. And so that, if you look at the graph on the left, the histogram, you can see that's what that's showing you. A lot of the data, a lot of the data, a lot of the data, and then the data starts spreading out. Slows down on it. That's what we see in the normal probability plot on the right-hand side. It's going to start off fast in the negative z-scores, and it's going to slow down in the positive z-scores. And we can see that over here as well, is we have the negative and it goes to the positive. It starts to be spread out more in that positive area. You can start to see that tail over in that positive area. So that's an example of what we're looking at here. Now, this is just showing you what it is. We have yet to even learn how to graph them, but you can see I've had my calculator up on the screen the entire time, so you are going to need that on it. But what we're going to do is this. To construct a normal probability plot, also known as a normal quantile plot, we can find the mean and standard deviation of data sets. So what does it mean? You know what? We can input, don't write this down. We can input all of our data in L1. And we can do a one variable stats for L1, and it will give us our mean, and it'll give us our standard deviation. Not too bad yet. We can calculate the z-scores for each piece of data. Wow. Yeah. So that means every single observation. We have to do it for every single piece of data. Every single observation. I got to calculate it. If I have a sample size of 30, I have to calculate 30 z-scores. I don't like that. Then we got to create a scatter plot, putting our vertical axis as our z-scores, our horizontal axis as our actual data values, and that's what we talked about here. You can see the labeling. You have z-scores on your vertical. You have your observations on the horizontal. So that, okay, that's not too bad. But then I got to plot all 30 of those. And I got to look to see if the pattern's linear. Normal distributions, approximately normal distributions, are going to have a linear pattern. Or, because this piece right here, and this is why I say don't write this down, that's a lot of work, number 2. We're not going to do that. We're just going to use our calculator. And if we're inputting it in L1, then let's have it do all the work for us. So what you need to do right now is make sure you get your calculator out. You can either pause the video or you can keep listening on it. Here's what I want to talk about while you're getting the calculator out. Let's think about what we've done so far. We know we're going to have to input our data. So my mind goes to stat edit, like it says on the screen. So when I input data, stat edit. But we also know we're creating a new graph of data, and that's where stat plot comes in. So I now know I need to go second y equals on it. So my mind's going through when I'm looking at this, if I need to input, stat edit, if I need a graph, stat plot. And then you want to make sure you use the correct graph and list for it. And so this screen was to remind me that we need our calculators. And so you can see, and this is what we're going to do. We're going to go to Stat Edit, we're going to go to Stat Plot, and we're going to choose our graph. And then we're going to examine from there. Now, you don't really have, if you take a look, too many examples on here of actually inputting, because it's really inputting the data. So we're just going to kind of look at my calculator to kind of help out for it. So we have here, and I am now invisible, but we have here the different things that we are looking at. And so when we go through, we are going to create our stat plot, so you can see everything. So we have stat, edit, haha. So what I have is I have 3 different lists. You don't need to type these in because you can look at the decimals, you don't even want to try. But I want you to just to pay attention to what I'm doing and kind of write down some notes that you have for this. Is you're going to input your data in L1. I inputted 3 of them, hence why I'm doing it this way. And then what we're going to do is we're going to look at stat plot. So I inputted numbers in L1, boom, it's done. I want to determine, is it approximately normal? So I'm going to go to second y equals stat plot. I'm going to turn on plot 1. So I'm going to hit enter, turn it on. So we have a scatter plot, we have a histogram, we have a box plot with outliers. Right here on the far right, that is your normal probability plot. So I want to make sure that is selected. I'm using list 1 for this first plot 1. And the rest, just make sure it matches on it, except for you pick your own color. And I'm going to hit, remember, zoom stat on it. So I'm going to hit zoom stat, zoom 9. And you look at that. That right there, if I were to analyze that, remember, these are your positive z-scores. These are your negative z-scores. These are your observations. Right here, I see a linear pattern along these lines, of almost linear pattern. So this data set, my L1 data set, I'm going to say is approximately normal. And we're going to get to this because there's important things still in your notes about that. So let's try a different one. So I'm going to hit second quit. I'm going to go to stat, edit. Now I also have another list, and this time it's in L2. This list, random numbers, again, don't try and type them in unless you want to have fun. And then when you go through, I now want to see, is that second list approximately normal? So again, I'm going to go to second stat plot. I'm just going to turn this one off. So boom. And then I'm going to go to plot 2. I'm going to turn plot 2 on. And again, you can still do it in plot 1 if you want. I just wanted to look at all different 3 ones. There's my normal probability plot. It's turned on. I'm looking at list 2. Let's graph it in red to have some fun and variety. And I'm going to hit zoom 9. And so there's that one. And so as I go through with this, and we're looking at these, we can see the different lists for it, and we look and see this one's a little bit different. It starts off right here, it's pretty slow in the negative z-scores on it. And then it starts to speed up right here. So it starts off pretty slow in the negative z-scores, which makes me think that this is going to be, if the negative z-scores are stretched out, this is going to be left skewed. And then it starts to speed up right here. So to me, that list 2 is left skewed because it's slow right here. It's spread out. It's a little bit longer on this side. So the tail is a little bit longer in the negative z-scores for it. Let's do second quit. I'm going to go to my stat, edit, and I input my list. This time I did it in L3, and I created a random list of numbers for it. I want to graph it. I'm going to go to second y equals. And I will turn off plot 2. And I'm going to activate plot 3. I'm going to turn it on. Again, I'm choosing the normal probability plot. My list is in L3. Changing the colors again to green, just to have fun. And then I'm going to hit zoom 9. So there's this set of data. Again, they were just random ones. I'm going to talk to you about what the graphs look like. And so you see right here, it's pretty fast. All your data right here in the negative z-scores are really close together. And then it spreads out in the positive z-score. So think about the curve. It's going to spread out in the positive direction. So I'm thinking that's right skewed. So you've seen 3 examples related to what you are dealing with on it. You've seen the approximately normal. You saw the right skewed. You saw the left skewed. So now Here, you should have some pictures as well. And you should be able to kind of see what we're talking about. And this is why it's really important to label what's going on. Then know what the y-axis is and know what the horizontal axis is going to help you when it comes to understanding the material that you're looking at and understanding which one is approximately normal, which one is right skewed, which one's left skewed. So I'm going to take a look at this. Let's label, because when you're sketching these, you do have to sketch the graph. You're going to have to label. You're going to have to pay attention like we've always done with sketching whenever we graph things. So we're going to do this. And so when you're looking at this, let's start labeling our axes. We learned from the beginning that these are your positive z-scores. Down here are your negative z-scores. The horizontal axis would be a z-score of 0 on it. And what your x-axis is, the horizontal axis, those are your data values. So what a normal probability plot really does is it plots the standard deviations away from the mean for each value in the data set. So if it's approximately normal, you should see a roughly linear pattern in the numbers. And we looked at that example. And so now what we're going to do is we're going to keep the bell in this instead of editing it. We're going to look at right skewed. And I want to sketch a right skewed. As it goes like this, and then it slowly tapers to the right on it. It stretches out on the right side. So what happens is the data is going to start off fast. You're going to have a lot of data. You're going to have a lot of data and a lot of data and a lot of data and a lot of data. That's what's going to happen on it. It's going to start off fast, and that's going to be in the negative z-scores. And then what happens is it's going to slow down, spread out. Look at it, slow down. The data is more spread out. It's stretching out on the right-hand side, which is the positive z-scores. And that's what we saw in those images that I pulled up on the calculator for it, is if we're looking for a right skewed distribution, it's going to start off, and I'm not going to plot points because then I have to erase all of them. It's going to start off, actually, you know what? I'm going to be consistent because I want you to do it right too. So let's do this. Boom, boom, boom. I'm going to start off by plotting points. So boom, 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 and I'm going to plot my points. And it's going to start off a lot of points down here. A lot, look at that. A lot of points, a lot of points, a lot of points, a lot of points. And then it's going to spread out in that tail on it. And that positive z-scores, has more spread in it. That positive z-score has more spread in it on a right skewed. So that's what a right skewed distribution is going to look like. So let's erase that. So left skewed might look a little bit different on it. So let's kind of think about that. A left skewed is going to have boom, 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 and so it's going to start slow for it. It's going to start pretty slow with what we're doing. Oh, sorry. So as I go through and we look at this, it's going to data will start off slow in the negative z-scores. So it's going to start off slow, it's going to be spread out, it's going to be spread out, it's going to be spread out. Then all of a sudden, we're going to be, bam, all the data is going to be there. And so what we're going to have is, we're going to have speeds up on it closer together in the positive z-score. So let's think about a left skewed distribution. It starts off slow in the negative z-scores. So we'll make this a little bit bigger. It starts off slow in the negative z-scores. They're spread out. And then it's going to be a lot of information here. That's a little too linear. Let's try this again. It's going to start off slow in the negative z-scores. Spreading out, spreading out, spreading out, spreading out. And then what's going to happen is it's going to speed up and be closer, 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 closer together. So we have more on there. We have more spread here. It's spread out. There's more tail here. That's what a negative z-score is going to look like on a left skewed distribution. So here's to keep in mind. Again, no real examples because I didn't want you typing in all of the information. What I did was I pulled up all of them here. Again, positive z-scores, starting off fast here, spread out in the positive z-scores, that's right skewed for it. As we go through, keep this in mind though, is dot plots, histograms, stem plots. Those are really, really good pieces of information for us. It reveals departures from normality, heavy skewness, gaps, clusters, potential outliers. That's what that does for us. Box plots, they do not reveal approximate normality. So look at that. That's the one thing missing here. It does not show approximate normality on these. It only shows us, for the most part, the idea of heavy skewness and actual outliers for it. What we learned today was a normal probability plot, and I want to talk about this one. Because when you graph, it's not just good enough to graph. You have to make a statement. You have to conclude from your graph. You have to assess normality from your graph. So what you need to make sure you do is do not just graph. Make a statement. What does the graph show you? After you graph, what does the graph show you? Answer that question. Write it down. Make sure the grader can see it. Communicate it to the grader. If the points lie close to a straight line, there is no reason to doubt normality. Since the normal probability plot appears to be approximately normal, there is no reason to doubt normality. Bam! You assess normality. You wrote it down for the grader. There appears to be a left skewness on the normal probability plot. Therefore, we cannot use approximate normal calculations. Bam! You communicate it to the grader. It is your job to not just graph, but also to state what that graph is telling you, to conclude what that graph is telling you, to communicate what that graph is telling you. That is your job as well. So this video went through the idea of assessing normality with a normal probability plot. I showed it on the calculator. Again, rewind, you can view that calculator again. It also wants to tell you is don't just graph. Remember, when you graph, I mean, look at this. I have the axes. I wrote down positive z-scores, wrote down my negative z-scores, and you're just going to graph. You don't have to plot each point. Maybe I should have said that before. You don't have to plot each point perfectly. You're going to get as close to it and approximate it as best as you can for it. It doesn't need to be all 30, 40, 50, 60 points. Don't need to be perfect plotted. Your graph needs to be approximate on it. So make sure you do that and then conclude what that means. Here's the good news. If you have managed to watch the past 23 minutes of this video, you are going to get a freebie with the 2.2 Quiz C. 2.2 Quiz C number 4 is your freebie for sticking around for 23 minutes, people. So here we go. We have 20 students. They're asked to guess the age of a man in a photograph, and here are their guesses on it. Are these guesses approximately normally distributed? Provide evidence to support your answers. So that's what we're asked. So right here, are these guesses approximately normally distributed? Well, that's a good question. You know what we're being asked to do there? We're being asked to assess normality. Determine if the data given to you is approximately normal. Provide evidence. Well, what type of evidence can I use? Now, in this case, what we're going to use is we are going to practice our normal probability plot. That's what we're going to use for this. So I'm going to at least sketch a little bit of my axes right now to help out, to think through. So a normal probability plot. I'm going to have a vertical axis. I'm going to have a horizontal axis. And the horizontal axis is going to be the z-score of 0. Above it are my positive z-scores. Below it are my negative z-scores. The x-axis itself are my data values. So what we're going to do is we're going to plot the average, the z-scores, the standard deviations for each value away from the mean. Calculator is going to do it for us. So we're going to go to our calculator. Boom. I'm going to go to Stat. I'm going to go to Edit. Lo and behold, I already have them typed in. So you can pause this video and type in all 20 of those numbers into your calculator. Again, you have to be able to do this. So pause. Type them in. Make sure you know how to create a normal probability plot in your calculator. After. So you paused. Pause. You typed them in. Now what do we do? I'm going to go to my second y equals my stat plot. I want to make sure there's only one plot turned on. So plot 3 is turned off, plot 2 is turned off, plot 1's turned on. I'll use plot 1 then. I'm going to hit enter. It is turned on. I have a normal probability plot highlighted from before, and my data is inputted in L1. So everything so far seems to be good. Again, stat edit, make sure you have these 20 numbers typed in. Second y equals stat plot. Plot 1, make sure you're choosing the normal probability plot. Make sure it's L1. Now we're going to hit zoom 9. Remember, zoom stat. And there's your data. So we are going to graph this. But again, that is a little, I'm not going to plot every single one of those points, all 20 of them. I want to make mine look as much as I can like that. So let's see if this works. Make it up as we go on the fly. And so when we do that, that is my image. It's not going to work, but I can do this. Boom, take this, I'll drop this over here. There's my picture. So I'm going to try and do this as best as I can. So I'm going to plot, we'll match it up just to be consistent, in blue. And so I'm going to plot here, looks like it. I'm going to plot here and here and here and here and here. And it's going to get a little bit there. Looks like it jumps up a little bit. All right, so there we are. And you know what? Haha, since I was off a little bit. Boom, done. Now, if I'm looking at that, and maybe mine is a little bit way worse than the calculator is that looks approximately normal. That looks like almost linear for it. It's got a linear pattern. So what do I say? Since the normal probability plot for, this is not a freebie, context, that's on you. What is the context of this problem? What do you need to put there? What does this data represent? That's your job, that context. Since the normal probability plot for context shows, displays an approximate linear pattern, it is safe for us to say it's approximately normal. It is safe for us to say it is approximately normal. And I apologize. I wanted to make this statement. It is safe for us to assume approximate normality for calculations. And that's way in the future, quarter 3. But there you go. That's what you're dealing with. Is you're looking at that information. Is since the normal probability plot for context on you shows an approximate linear pattern, it is safe for us to say it is approximately normal. By the way, what if it didn't show it? What if it was skewed? Well, since the normal probability plot for context shows a left skewed pattern, it is not safe for us to assume normality. So it's one of those things where that's on you. So you stuck around for 23 minutes and you got a freebie, number 4 on 2.2 Quiz C. Thank you. Like and subscribe.